The universe is full of wonders, both visible and invisible. While our eyes perceive a world of shapes and colors, there exists another realm, hidden from direct view, the realm of fields. These fields, like invisible threads, weave together the fabric of reality, dictating how objects interact and energy flows. Among them, scalar fields stand out for their simplicity and elegance, underpinning many phenomena we encounter daily. Imagine a warm summer day. You feel the sun's heat on your skin, a tangible manifestation of temperature. What you're experiencing is a scalar field in action. At every point in space, a specific temperature exists, represented by a single number, a scalar value. This value can change from place to place and over time, creating a dynamic tapestry of warmth and coolness. Scalar fields are more than just abstract concepts. They are essential tools for understanding the universe at its most fundamental level. From the behavior of subatomic particles to the evolution of galaxies, scalar fields play a crucial role in shaping the cosmos as we know it. This exploration into scalar fields will unveil their hidden beauty and far-reaching implications, demonstrating how these invisible entities govern the world around us. Scalar fields are not confined to the realm of theoretical physics. They permeate our everyday experiences. Take, for instance, the air we breathe. It exerts pressure on us, a force we rarely notice but constantly experience. This pressure, like temperature, is a scalar field. At any given point, air pressure can be quantified by a single value, varying with altitude and weather patterns. Consider a map showing elevation contours. Each contour line connects points of equal altitude, effectively depicting a scalar field, the gravitational potential energy. This energy, determined by an object's height above the Earth's surface, dictates how easily it can fall. Another familiar example is the concentration of sugar in a cup of coffee. Before stirring, the sugar density is highest at the bottom, gradually decreasing towards the top. This concentration gradient, a scalar field in its own right, drives the sugar to dissolve and distribute evenly throughout the coffee. These examples illustrate the ubiquity of scalar fields in our daily lives. From the warmth of the sun to the pressure of the air we breathe, scalar fields shape our sensory experiences and underpin the workings of the natural world. Mathematically, a scalar field is defined as a function that assigns a single scalar value to every point in a given space. This space can be one-dimensional, like a line, two-dimensional, like a surface, or three-dimensional, like the space we inhabit. The scalar value can represent any physical quantity that can be described by a single number, such as temperature, pressure, density, or energy. For instance, we can represent the temperature distribution in a room using a scalar field, T, X, Y, Z, where X, Y, and Z represent the coordinates of a point in the room, and T, X, Y, Z gives the temperature at that point. This function assigns a single temperature value to each point in the room, effectively mapping out the temperature distribution. The mathematical framework of scalar fields provides a powerful tool for describing and analyzing various physical phenomena. By representing physical quantities as scalar fields, we can apply the tools of calculus and other mathematical disciplines to study their behavior and relationships. This mathematical rigor allows us to move beyond qualitative descriptions and delve into the quantitative analysis of scalar fields, uncovering deeper insights into their properties and implications. While the mathematical definition of scalar fields provides a precise description, visualizing these fields can be challenging. Fortunately, several techniques allow us to represent scalar fields graphically, making them easier to comprehend and analyze. One common method is the contour plot, as seen in topographic maps. In a contour plot, lines connect points of equal scalar value. For instance, in a temperature map, lines called isotherms connect points with the same temperature. The spacing between contour lines indicates the rate of change of the scalar field. Closely spaced lines represent a rapid change, while widely spaced lines indicate a gradual change. Another powerful visualization technique is the heat map. In a heat map, different colors represent different scalar values. For example, in a temperature map, warmer areas might be represented by red and orange hues, while cooler areas are represented by blue and green shades. The intensity of the color can also represent the magnitude of the scalar value, providing a visually intuitive representation of the field's distribution. These visualization methods provide valuable insights into the behavior of scalar fields. By examining contour plots and heat maps, we can identify regions of high and low values, gradients, and other important features, facilitating a deeper understanding of the underlying physical phenomena. Section 5. Scalar versus vector fields, understanding the difference. While scalar fields associate a single value with each point in space, vector fields add another layer of complexity. They assign both a magnitude and a direction at every point. Imagine a wind map. Each point has an arrow indicating wind speed, magnitude, and direction. This is a vector field in action. The distinction between scalar and vector fields is crucial. Temperature, being a scalar, is independent of direction. Whether you move left, right, up, or down, the temperature changes by a specific amount. However, wind, a vector, changes drastically depending on your direction relative to its flow. This difference in directional dependence leads to distinct mathematical treatments and applications for scalar and vector fields. Understanding their unique characteristics is essential for accurately modeling and analyzing various physical phenomena. While scalar fields provide information about the intensity or concentration of a quantity, vector fields reveal how this quantity flows and interacts with its surroundings. Section 6. Delving deeper gradient and Laplacian of scalar fields. To further unravel the secrets of scalar fields, we delve into two essential mathematical operations: gradient and Laplacian. The gradient, denoted by the symbol nabla, reveals the direction and rate of the scalar field's fastest change. Imagine climbing a hill. The gradient points uphill in the direction of the steepest ascent. The Laplacian, denoted by 2, provides insight into the field's source and sinks. It measures the difference between the field's value at a point and its average value at neighboring points. A positive Laplacian indicates a source where the field is generated, while a negative Laplacian suggests a sink, where the field is absorbed. These operations are crucial for understanding how scalar fields behave and interact with other fields and objects. For instance, in electrostatics, the electric potential is a scalar field, and its negative gradient gives the electric field a vector field that dictates the force on a charged particle. By applying these mathematical tools, we can extract valuable information about the behavior of scalar fields, leading to a deeper understanding of their influence on the physical world. Section 7. Scalar fields in physics, gravity, electromagnetism, and more. Scalar fields play a fundamental role in physics, underpinning some of the most fundamental forces in the universe. Gravity, for example, can be described using a scalar field called gravitational potential. This field determines the gravitational force experienced by an object at any point in space. Electromagnetism, another cornerstone of modern physics, also relies heavily on scalar fields. The electric potential, a scalar field, determines the potential energy of a charged particle at a given point in an electric field. Similarly, the magnetic scalar potential, while less commonly used, simplifies the analysis of magnetic fields in specific cases. Beyond these fundamental forces, scalar fields are crucial in quantum mechanics, describing the behavior of particles at the atomic and subatomic levels. The Higgs field, a scalar field, is responsible for giving particles their mass, a concept central to our understanding of the universe's structure. From the largest scales of cosmology to the tiniest realms of quantum mechanics, scalar fields provide a unifying framework for describing the fundamental forces and particles that govern the cosmos. Section 8. Scalar fields in engineering and technology. The applications of scalar fields extend far beyond theoretical physics, finding widespread use in various engineering and technological disciplines. In civil engineering, for instance, understanding the scalar field of stress and strain is crucial for designing safe and stable structures. Engineers analyze these fields to ensure bridges can withstand the weight of vehicles and buildings can resist the forces of wind and earthquakes. In mechanical engineering, scalar fields are essential for studying heat transfer and fluid flow. Analyzing temperature distributions helps engineers design efficient engines, optimize cooling systems, and develop effective insulation materials. Similarly, understanding pressure and velocity fields is crucial for designing aerodynamic vehicles and efficient pumps and turbines. The realm of electronics and telecommunications also benefits significantly from scalar fields. Signal strength, for instance, can be represented as a scalar field, allowing engineers to optimize antenna placement for maximum coverage and signal quality. Understanding the distribution of electromagnetic fields is crucial for designing efficient antennas, waveguides, and other electronic components. From designing sturdy structures to optimizing communication networks, scalar fields provide engineers with invaluable tools for solving real-world problems and advancing technological innovation. Section 9. Scalar fields in other disciplines, from medicine to finance. The reach of scalar fields extends even further, influencing disciplines as diverse as medicine, finance, and meteorology. In medical imaging, techniques like magnetic resonance imaging, MRI, rely on measuring the response of atomic nuclei to magnetic fields, which can be represented as scalar fields. By analyzing these fields, doctors can visualize internal organs and tissues, aiding in diagnosis and treatment planning. Meteorologists use scalar fields to represent atmospheric pressure, temperature, and humidity. These fields are essential for predicting weather patterns, understanding climate change, and issuing severe weather warnings. By analyzing the evolution of these fields, meteorologists provide crucial information for agriculture, transportation, and public safety. Even in finance, scalar fields find applications in modeling stock prices, interest rates, and other economic indicators. By representing these variables as scalar fields that evolve over time, financial analysts can develop sophisticated models to predict market trends, manage risk, and make informed investment decisions. The versatility of scalar fields allows them to transcend disciplinary boundaries, providing a unifying framework for understanding complex phenomena across various fields of study. Section 10. Conclusion: the pervasive influence of scalar fields. From the invisible hand of gravity shaping the cosmos to the intricate dance of electrons in our smartphones, scalar fields permeate every facet of our existence. While often hidden from plain sight, their influence is undeniable, shaping the world around us in profound ways. Understanding scalar fields is not just an academic pursuit. It's about grasping the fundamental language of the universe. Whether you're a physicist unraveling the mysteries of the cosmos, an engineer designing innovative technologies, or simply a curious mind marveling at the wonders of the natural world, appreciating the elegance and power of scalar fields enriches our understanding of the interconnectedness of all things. As we continue to explore the universe, both within and beyond our reach, scalar fields will undoubtedly play an increasingly important role in shaping our understanding of the cosmos and our place within it. Their story, a testament to the power of simple yet profound concepts, is far from over, promising exciting discoveries and technological advancements for generations to come.